Picture this. You're sitting in the exam hall. The silence in the room is deafening, and all you can hear is the clock ticking down on the wall. You turn the page of your Cambridge physics past paper, syllabus code 0625, and there it is, the ultimate boss battle of the exam, a high-stakes multi-part question on energy transfers. Now, this is the exact moment that separates the good students from the truly exceptional ones. What really separates a B from an A-star in physics? Well, let me introduce you to two students who represent exactly what we see year after year. Let's call them Alex and Sam. Now, Alex is what we call an overloader. Alex sees a question about an electric motor lifting a heavy load and immediately panics. We're talking a massive brain dump. Alex writes down every single raw physics fact about electricity, gravity, forces, you name it. Zero analysis, absolutely no structure, just a giant wall of text hoping something, anything, sticks to the mark scheme. And then we have Sam. Sam is the rusher. Sam looks at the exact same question, punches some numbers frantically into the calculator, slaps down a final answer, but completely misses the command word requirements. The question specifically said calculate and explain, but Sam just calculated. No working out shown, no method, nothing. So what happens? When the results come back, their papers are literally bleeding red pen marks. They've missed out on those absolutely crucial method marks, also known as M marks, and just like that, both of them drop from a potential A-star to a B. Not because they don't know the physics, but because they simply don't know how to play the game. Okay, let's dive into this and change that outcome for you today.
A senior Cambridge examiner recently made an observation that honestly changes everything. They said, the difference between a B and an A-star in physics often comes down to how well you understand work. Mechanical or electrical work done equals energy transferred. W equals FD equals delta E. Now, listen to me carefully here. This isn't just an equation you memorize, it's the ultimate bridge in physics. It is literally the Rosetta Stone of the entire syllabus. Whether you're dealing with mechanics, electricity, or thermodynamics, energy transfer is the universal currency of the universe. If you can master how to communicate this exact principle, how mechanical work, like pushing a heavy box across the floor, is fundamentally the exact same thing as electrical work, pushing electrons through a circuit, you unlock the absolute top tier of marks. You see, examiners aren't just looking for you to state the formula like a robot, no way. They are hunting for candidates who exhibit connected, conceptual understanding that transfers seamlessly to completely unfamiliar contexts.
Welcome to today's Explainer, brought to you by the Engineering Lab. Today, we are focusing entirely on physics Cambridge exam strategy. And it doesn't matter if you're tackling the IGCSE 0625, the 0651, the 0652, the O-Level 5054, or even looking ahead to the rigorous A-Level 9702. The principles we unpack today are your absolute blueprint for success. We are going to build bulletproof arguments with stress-tested evidence and serious quality control. We're going to take those red pen corrections that Alex and Sam got, and we're transforming them into green check marks. My goal today is to give you the exact behind-the-scenes examiner playbook so you can walk into that exam hall with total, unshakable confidence.
Let's completely ground ourselves in the fundamental formula. W equals FD equals delta E. What's really fascinating about this formula is just how much incredible information is packed into a few simple letters. W is the work done, measured in joules. F is the force applied in newtons. And D is the distance moved in the specific direction of the force, measured in meters. That's your mechanical side, the physical pushing and pulling. But then we have the incredibly crucial equals delta E, the change in energy. This right here is where the magic happens for electrical work too. When a power supply does electrical work, it transfers energy to the components in a circuit. The beautiful thing about this definition is that it forces you to think about the universe as a giant accounting system. Energy cannot be created, it cannot be destroyed, it is merely transferred from one ledger to another. When you do work on an object, you are transferring energy to it. When an electric motor does work, electrical energy is being transferred into kinetic and gravitational potential energy. Top students, the ones getting the A-stars, they don't just memorize the letters, they visualize the transfer happening in real time.
So here is our visual roadmap for today's explainer. We're hitting 4 crucial steps to secure those vital method marks. We'll cover the A-star physics blueprint, mastering technical methodology, the deconstruct, solve, evaluate framework, and finally, those top examiner warnings.
Section 1, the A-star physics blueprint. We're going to look at targeting specific cognitive domains to understand what Cambridge actually wants from you academically.
Look at this table. The crucial point for exam success is right here in these assessment objectives. Column 1, knowledge and understanding. This is the absolute bare bones foundation.
Can you recall the formula W equals FD equals delta E? Can you state the units? That's your basic recall. But Cambridge doesn't hand out A stars for just having a good memory. That brings us to column 2, application. This is where you actually use that knowledge in a familiar or even slightly unfamiliar context. For instance, calculating the work done by a massive crane lifting a steel beam on a construction site. Finally, we have the Holy Grail, column 3, analysis. This requires logical, structured reasoning. The assessment framework prioritizes analytical depth over superficial breadth. This means looking at a complex scenario, like a car slamming on its brakes, where kinetic energy transfers to thermal energy via work done by friction, and being able to break down the relationships mathematically and conceptually. To hit all 3 domains perfectly, top students use the PEEL framework for descriptive answers. P-E-E-L, point, evidence, explanation, link. You make your point about the energy transfer. You provide evidence from the data or diagram, you explain the physics principle, and you link it back to the specific question asked. If our friend Alex the Overloader had used PEEL, there wouldn't be a messy brain dump. There would be a structured, analytical response that examiners love. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Moving into Section 2, Mastering Technical Methodology. We're going to focus heavily on data interpretation and application, because knowing the theory is one thing, but using it under pressure is another. All right, there are 5 professional skills you absolutely need for practical application to pull data from text and tables. First, applying correct formats. If you are calculating work done, you must state your final answer to the appropriate significant figures, usually matching the lowest number of sig figs given in the data, and you must include the unit, joules. Second, using appropriate terminology. Please, never write energy is used up. Physics teachers literally cringe at that. Say energy is transferred or work is done against friction. Third, evaluating performance. If an electric motor's input electrical energy is greater than its useful mechanical work done, you need to evaluate its efficiency and explain where the lost energy went, usually dissipated as heat to the surroundings. Fourth, interpreting relationships. If a graph shows force on the y-axis and distance on the x-axis, interpreting that relationship means instantly recognizing that the area under that curve equals the work done. Finally, drawing evidence-based conclusions. You must look at the data tables provided and use those exact numbers to support your written statements. Let's go back to our student Alex for a second. Let's say we sit Alex down, give him these bullet points, and have him rewrite his answer. Instead of a messy brain dump, Alex now writes a clean PEEL paragraph. The motor transfers 500 joules of electrical energy. As the load is lifted 2 meters, a force of 200 newtons is applied. Calculating W equals FD, the mechanical work done is 400 joules. Therefore, 100 joules is dissipated as thermal energy, showing an efficiency of 80%. Boom! We just went from red marks to green check marks. That is the physics success blueprint in real-time action.
Let's jump into Section 3, Deconstruct, Solve, Evaluate. This is the ultimate problem-solving framework that top students use to systematically secure every single point. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's walk step by step through this precise deconstruct, solve, evaluate sequence. This is exactly what examiners look for when awarding method marks. Step 1, identify given information. Scrape the question for data and write down your variables on the side. F equals 50 newtons, D equals 10 meters. Step 2, break into logical steps. Decode the command word. If it says calculate, you need the formula, W equals FD. Step 3, solve systematically. Substitute the numbers into the equation before you manipulate the algebra. Show you're working clearly. Step 4, check for reasonableness. Look, if you calculate the work done by a human lifting a small box and you get 5 billion joules, something is wildly wrong. Check your units. Did you forget to convert centimeters to meters? Step 5, make justified recommendations or conclusions based on the result. Okay, it is time for our interactive workshop. I want you to mentally engage with this right now. Challenge 1, data scan. Imagine a complex data table on your screen showing a car's braking distance at different speeds. I'm putting 60 seconds on the clock in my head right now. What is the core trend? Think about it. As speed doubles, what happens?
Kinetic energy quadruples because Ke equals half mv squared. Therefore, the work done by the brakes must quadruple, meaning the braking distance quadruples if the braking force is constant. If you can extract that trend from a table under time pressure, you are thinking exactly like an A-star student.
Now this brings us to the most critical examiner alert we can possibly give you. We are talking about generic versus context-specific answers. Consider a generic textbook answer. Work is done when a force moves an object. Energy is transferred. Okay, that's true, but it's broad. It's unspecific. In an application question, that earns exactly 0 marks. In contrast, consider a context-specific answer. Work is done by the electric motor against the gravitational force of the elevator. Electrical energy from the mains is transferred into the gravitational potential energy of the elevator system. Do you see the difference? It's perfectly linked to the scenario. All right, challenge 2, find the flaw. Listen very closely to this sample physics paragraph and tell me where they lose marks. The battery does work on the circuit. W equals delta E. The bulb lights up because energy is created. Did you catch the flaw? I hope you did. Energy is never, ever created. It is transferred. The battery transfers chemical potential energy into electrical energy, which does work on the bulb, transferring it to light and thermal energy. Always, always link every single point to the specific context given in the scenario.
This brings us to the higher order skills. When a question asks you to evaluate alternatives or compare approaches, let's say comparing an electric vehicle's motor to a standard internal combustion engine, you absolutely need these comparative analysis requirements. You must identify similarities and differences. For example, both transfer stored energy into kinetic energy doing mechanical work. But the electric motor transfers electrical energy, while the internal combustion engine transfers chemical energy through combustion. You must use comparative connectives like whereas, conversely, or in contrast. You need to support your comparisons with hard evidence, use the numbers from the data, and finally, draw conclusions on relative importance, such as pointing out which system is actually more efficient based on the calculated delta E. Okay, challenge 3, speed writing. Imagine you have 30 seconds to write one perfect PEL paragraph, comparing the work done by 2 different machines. You would start with your point, machine A is more efficient. Then give your evidence, it requires less electrical input to perform the same mechanical work. Then explain the physics. Less energy is dissipated as heat due to friction, and finally, link it back to the question's demand. That structured sequence is exactly how you completely master the examiner's standardized assessment rubric. Let's shift to our final, and honestly, perhaps most vital section, Section 4, Top Examiner Warnings Revealed. We have dug deep into the Cambridge Principal Examiner reports to uncover exactly where students lose marks. Here they are, the absolute top 3 mistakes directly from the people who actually grade your papers. Number 1, confusing cause and effect. This happens all the time. Students often write that the kinetic energy caused the work to be done, when in reality, the work done on the object caused the change in kinetic energy. W equals delta E means the work results in the energy transfer. You must be precise with your language. Number 2, forgetting to check format and presentation. Remember our friend Sam from the beginning? Sam did the math but totally rushed the presentation. No clear working, missing the unit joules, or leaving the answer as some messy fraction instead of a standard decimal. Listen to me, examiners cannot give you method marks if your method is illegible, period. Number 3, providing answers not specific to the context given. As we just discussed, dropping generic textbook definitions into a highly specific scenario is a trap. If the question is about a massive wind turbine, you need to talk about the kinetic energy of the wind doing work specifically on the turbine blades. Don't just talk about generic forces. You absolutely must adapt your knowledge to the specific reality of the question paper in front of you. So, we arrive at our final challenge today, building your complete system. Remember the 3 rules that guarantee top marks: command word decoding, applying the PEL framework, and using a time management matrix to avoid rushing like Sam. To lock this all in, I want you to create your own memory hack right now. A mnemonic so work equals force times distance equals change in energy. Something that powerfully links the mechanical and electrical realms in your brain. Maybe something like, when forces drive, energy shifts. Play around with it. The physical act of creating a memory hack literally builds neural pathways that make your recall under exam stress instantaneous. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.